This video, you're looking at a screen, but actually all you're really taking in is atoms, arranged in a very particular way. Look away from your screen and you might see a book, an apple, a swimming pool, a rhinoceros, anything, and it's exactly the same deal. Certain atoms built and arranged in certain ways so that on our level we understand them as whatever it is that they've amalgamated to be. But of course, the atomic structure of something, be that the water you drink, the atmosphere you breathe, the cake you bake, and so on, is always key. Underneath it all, even you yourself are only atoms. Human beings are an especially complex mass of atoms, yes, but still, that's all that we really are. In the old days, stereotypically wise figures might have dabbled in alchemy. In short, alchemy was like an attempt to try to control atoms even before the discovery of them, and mostly to try to turn one thing into something else. Usually gold, but that's besides the point. Because today, broadly, we know that same pursuit, that same attempted mixing up of materials as chemistry. And in the modern world, we really can break down all or most materials into their fundamental parts, and even in some cases, we can rearrange them. Again, it's merely a case of having the right atomic knowledge, no alchemy needed. But still, we've only had this level of knowledge for the past century or so, and it's been a long time coming. Theories on a base level of matter do date back far earlier, to the times of ancient Greece, and particularly to one 5th century BCE philosopher, Democritus. He wrestled with an idea. If you have something and cut it in half, and then half again, and then again, and again, and again, indefinitely, would you eventually reach a point where what was left could no longer be cut? Would you eventually reach a kind of starting point for matter, a base unit, below which it was impossible to go? This hypothesized unit was then labeled an atom, with the word deriving from the Greek atomos, which means uncuttable or indivisible. However, from there, this really revolutionary idea was effectively shelved for a couple of thousand years. It's not until the early 1800s that atomic theory properly takes hold again, thanks mostly to one John Dalton. His most famous contribution to science is the law of multiple proportions, otherwise known as Dalton's law, first put forward in 1804. Through it, Dalton realized that the masses of simple chemical compounds could always be reduced back down into ratios with small whole numbers. More simply, Dalton was able to show that whenever, say, oxygen were present, it was possible to calculate how many parts or units of oxygen there were based on mass. The structure of a compound, although far too small to be seen, could always be determined. The difference between, for example, carbon monoxide and carbon dioxide could now be explained. Dalton didn't have it all correct from the beginning, though. At this stage, it was still thought that there was nothing smaller than the atom. But we now know that that's wrong. We know, for instance, that an atomic nucleus is made up of protons, neutrons, and electrons, subatomic objects that further serve to differentiate one element from the next. But still, Dalton's work is widely held to be the beginning of atomic theory. He picked up from where the ancient philosophers left off, and built a base from which emerging physicists could work and experiment in the 19th and 20th centuries. Unsurprisingly, and almost exactly 100 years after Dalton's law was introduced, Albert Einstein enters the fray. In fact, Einstein's explanation of something called Brownian motion, the seemingly random movement of particles when suspended in water or gas, goes down as one of his first major scientific achievements. Einstein suggested that Brownian motion was quite simply caused by the movement of countless other and smaller particles that surrounded the larger and more noticeable ones. This, again, was something of a game changer, as it encouraged us to think not just of objects, but of reality as a whole, as though it were one swirling, connected, interacting mass of atoms, which ultimately it is. Visual depictions of Brownian motion are somewhat headache-inducing, but that's what makes it all the more incredible that this almost vibrating hum of particles should be happening all the time, all around us. From the late 1800s through to the First World War, physicists including J.J. Thomson, Ernest Rutherford, and Niels Bohr worked to incorporate the newly discovered electron, discovered by Thomson, into the then ever-changing model of what an atom actually looked like. By the time of the Second World War, that model had been put to such use that we were now capable of splitting the atom via nuclear fission. The most infamous result of this being the advent of the nuclear bomb. Around this time, and especially with the war effort on both sides driving research forwards, a number of high-profile scientists were involved in the development of nuclear physics, including still Albert Einstein, plus Enrico Fermi, Leo Szilard, and Robert Oppenheimer. Unsurprisingly, and mostly due to the bomb, experimentation with atoms became something that some people feared post-World War II. One of the difficulties was that, although high-ranking physicists now understood the atom better than ever before, it remained something of a mysterious commodity for everyone else watching on. As we move through the 21st century, much of that fear factor has disappeared, perhaps simply because subatomic study is such a standard backdrop to contemporary life. Although, that said, we do still see various examples of rising panic, such as when the Large Hadron Collider was first switched on at CERN, and many worried that it would instantly create a black hole on Earth and spaghettify us all into an early death. Thankfully, that didn't happen, and subatomic science has now fully made its latest jump into quantum mechanics. If the atom is hard to visualize, then the quarks and leptons of the subatomic quantum realm are even harder. But thanks to the standard model of elementary particles, we do at least have a structure to refer back to. The model is being continually updated as researchers make more and more breakthroughs as the result of work at facilities like the LHC, with one of the most famous achievements in modern times being the successful detection of the Higgs boson, the so-called God particle, in 2012. It makes you wonder, what would John Dalton make of today's advancements? No matter how much more we achieve, however, perhaps nothing will eclipse the scale of the shift uncovered by the likes of Dalton from the early 18th century onwards. Before atomic theory, we didn't yet know quite how much of a mystery the physical world really was to us. We were largely ignorant to its inner workings. There had, of course, been countless methods and tricks discovered wherein the chemical makeup of our surrounding materials were already being manipulated. We see it in the cooking of meals, the making of drinks, the building of houses, towns, and cities. Whenever anything, any object, material, liquid, or gas is altered on a macro visual level, there's some kind of atomic restructuring taking place down below. But those early scientists were the first to truly grasp this, and their realization forced us all to view reality itself completely differently. Now we're busy fleshing out even lower levels via the standard model, but still, the atom itself is the original and greatest watershed moment. A before and after point in time from which we launched into an all-new age for science and technology. And that's how we